All right, so here we have Orion, and we have some cultural significance. Actually, we've been able to analyze this a little more closely using, of course, the good old Space Telescope, but we now understand a little bit more about what the true significance of it gets, and it's not pleasant. It's going to get worse than this. But anyway, we see obviously now you're thinking. I know what you're thinking. Who's this going to be? I know what you're thinking. You don't even have to say it. I know exactly what you're thinking. It starts with B, capital B. But surprisingly, no. This really just surprised me because I seem to have some anger management problems, but I never really.
You really shouldn't threaten my sister like that, you know.
Okay, whatever.
Yeah! No!
I forgot about that part. I just can't resist those little fingers once in a while. All right, so I'm going to give you a little more detail about this cosmic coordinates. They're actually filming me this year, by the way. It's going to be interesting to see how much of this gets into the online course. Can't wait to see the director's cut. All right, so the cosmic latitude-longitude system that we're using in the celestial sphere is actually declination and right ascension, which I've already mentioned. Declination is real simple. It's just like normal latitude on the Earth. We do have to keep in mind that the whole coordinate system spins with the stars, but basically, declination is like latitude on the Earth. So we can indicate regions in the northern half of the celestial sphere. We have positive declinations from 0 at the equator to 90 straight up, and then negative 90 for the south. I think this slide is in the online notes, so I hope you're not really working too hard to write all this down. Pretty sure this one is in there. So if we look at Betelgeuse and Orion, that's actually the red giant star I pointed out to you. In the shoulder of Orion has a declination of 17 degrees, so it's in the northern half of the celestial sphere. The right ascension works like longitude, but again, it uses these unusual units of time units because we want to have the sky sweep through 24 hours of right ascension and 24 hours of clock time, so that everything, we're trying to make the sky work like clockwork, basically. That makes it a little bit easier for us to track the positions of objects in the sky. Okay, so we measure right ascension in time units, and if we just look at a fixed point in the sky, what we're going to see is the coordinate system is going to sweep through 1 hour of right ascension coordinate for every hour of actual time. So again, if you just picture, you gaze at a certain point in the sky, you're looking at a certain set of coordinates right now. If you wait an hour, you'll still be looking at the same declination line, but the right ascension will have shifted by an hour, and you'll be seeing different stars that have 1 more hour of right ascension as their coordinates. It's kind of like you're looking down at the Earth, and the Earth is spinning, and so you're looking at different continents or something because of the spin of the Earth. Okay, so here's this little multimedia extravaganza where I build up the whole concept of the celestial coordinate system. It basically starts with the Earth, its spin axis, and its equator. Okay, so the Earth, by the way, you should remember, spins counterclockwise as viewed from above the North Pole of the Earth, which we actually call the North Celestial Pole up here. The North Celestial Pole is very, very high above Earth's North Pole. If you look down, at the top of St. Joseph's Workshop there, you're going to see counterclockwise spin. Now, these lines are lines of constant right ascension. So every one of these lines has a fixed right ascension value from 0 to 24 hours, and this whole thing, of course, would spin. So it spins with the stars. So these stars actually have specific right ascension values, and now we lay on these other great circles, which are these circles of constant declination. And so any one of these circles is a circle of constant declination. And then we can put numbers on these things as well. And we can even put the ecliptic on and start talking about the units of right ascension. But anyway, so here we see units of declination from positive 90 at the North Celestial Pole to negative 90 at the South Celestial Pole. I put the celestial, the ecliptic right there. The vernal equinox is a special point because you might be wondering, where is the 0 of right ascension? It has to be some place. I mean, basically some star or group of stars has to have 0 right ascension. So how would we choose which direction is 0 right ascension? It could be any direction in the sky. Well, we actually tie that back to the sun. The 0 right ascension point is defined as the point where the ecliptic crosses the celestial equator. And the sun is on that point at the vernal equinox. So in the spring, around March 21st, the sun is sitting right on that point where the right ascension is 0 and the declination is 0. That special point. And that's how we set up our coordinate system. And then we can also, again, put the hour units on the specific things. I didn't have the technology to get this thing to actually spin around, unfortunately. Not that savvy for PowerPoint. But if we pick that star right there, it's got a declination of, say, around 40 degrees, roughly, between 30 and 45. So let's say it has a declination of about 40. Has a right ascension of 12 hours of right ascension. So if I was to be able to animate this thing, I'd get the counterclockwise spin. And if we keep looking at that point in the sky, that star would drift away. But we would actually still be looking at new stars that come into that point. But all the stars that sweep in will still be at 40 degrees of declination. Because, for example, if I just stare at that blue line right there, 45 degrees of declination, if I just keep looking in that direction and I lock my telescope, I'll keep seeing things that have 45 degrees of declination, but different right ascension values over the 24-hour cycle. Oh yeah, here, this we can animate. So now we're looking out in the sky. We're looking north. So this is looking north in the northern hemisphere. And we're able to see Ursa Major, minor over there. You have Ursa Major down here. And you can see it's mainly the Big Dipper shape right there. That's Big Dipper, the Small Dipper, Ursa Minor. The pole star Polaris is the end of the Small Dipper's handle, and that's basically the direction of the North Celestial Pole. Now notice there are specific coordinates again here. We have each of the spokes radiating from the center has a definite right ascension value. That's its coordinate. So all the stars living along this spoke right here from the center, all of them have 18 hours of right ascension, but they have different declination values. And the declinations are indicated here. So, for example, Polaris has just about exactly 90 degrees of declination. And as we move away, we're seeing that the Big Dipper itself is sort of around maybe 65. The Dipper is about 65 declination and about 15 hours of right ascension. And it'll keep those coordinates. So if I let this move, we'll see the stars spin counterclockwise around the North Celestial Pole, and we'll see the coordinates spin with the stars, because the stars keep their coordinates. So the whole thing moves like this, right? So we're actually seeing the diurnal motion, and Ursa Minor, the bucket there, the Little Dipper, is dragging the coordinate system with it. So the bucket is still at about 60 degrees of declination and 15 hours of right ascension, and it's just moving all the way around. And if we wait 24 hours, it'll have rotated back to the starting point. So if we look at a fixed point in the sky and we keep looking at that point, for every hour of time, we're actually seeing the same declination, but objects with one more hour of right ascension. So we're kind of riding on one of these great circles because of the way the coordinate system is designed to operate. Okay. So here's another example where we actually have a telescope. So we're pretending there's a telescope pointing to the sky, and we start rotating. You can see the telescope is seeing objects at 60 degrees of declination. Everything it's looking at is at 60 degrees of declination, but more and more hours of right ascension because it's just spinning like a clock, essentially, right? 24 hours, we'll be back to seeing the original stars we were looking at. But during this whole time, we're still seeing the same declination value. All right, so just a word about units of arc measure that we use in the course. There's a couple of different ways that angles come into the course. We usually start with the idea of degrees, of course. There's 360 degrees in a circle, so that's true. You know, this is true in astronomy, there's in geometry or anything else. We start at 360 degrees in a full circle. Each of those degrees is divided into 60 arc minutes. This is actually one single degree. Kind of run out and made larger in size. Now over here, we're indicating 1 arc minute. That blue line is 1/60th of the full width. So we start with 360 degrees. Each degree has 60 arc minutes. You notice I got to say arc minutes because we're not talking about time units here. These are angular units. An arc minute is 1/60th of a degree. But then we subdivide that even further. One single arc minute is divided into 60 arc seconds. And you got to have arc in there, or again, it doesn't make sense because you're comparing units done at the right dimension. So there's 360 degrees in a circle, 60 arc minutes in a degree, and 60 arc seconds in an arc minute. Therefore, how many, for 2 points, how many arc seconds are there in a degree? Arc seconds in a degree. 3,600, 2 points, this thing right here. We'll need to keep track of that. Okay, so there's 3,600 arc seconds in one single degree, and if you want to multiply by 360, you get however many there are in a circle. I actually don't know what that is, but there's lots and lots of arc seconds. Now, the arc second is pretty relevant for us in astronomy because as a unit of angular measure, it also starts to get into the issue of how large features you can see on something. We'll actually get into that more when we get to the chapter on telescopes. But we do have to get into the difference between the sidereal day and the solar day. And this is actually still connected with the idea of solar motion. As I mentioned, when we look out at the stars and we let the whole pattern spin, like we just saw, the pattern spun around, and after one full cycle, the stars looked like they were exactly back at their starting point. That actually wouldn't be 24 hours of normal clock time. Normal clock time is set on the solar cycle, which is the time between noons at a location on Earth. The time between noons isn't exactly the same as the time between